Walk deep into the Gobi Desert, and you'll find places seemingly stripped of life. No rivers, no birds, just an endless expanse of golden sand, sitting in absolute, unbroken silence. Until the ground beneath your feet erupts. The air begins to shake with a deep, powerful vibration, rising from the dunes. This chart shows how loud that vibration actually gets. A normal conversation sits at 60 decibels. A motorcycle pushes 95. The roar of these singing dunes hits up to 105 decibels, approaching the volume of a low-flying aircraft. This immense noise is generated in an environment that is completely devoid of machinery, electronics, or living creatures. For centuries, travelers crossing these landscapes reported hearing these noises rising from nowhere. Merchants following the ancient Silk Road, and later explorers like Marco Polo, documented a desert that seemed entirely alive. Ancient Chinese records detail the terror of these encounters. With no logical explanation for the sound, early travelers attributed the noise to invisible armies, angry spirits, or demons buried beneath the dunes. It presents an intriguing physical paradox. How can a static pile of rocks and dust create a deafening, sustained acoustic wave with absolutely no moving parts? To find the source of that massive roar, we have to abandon the old ghost stories and look much closer. If you dive past the sprawling dunes and look closely at the sand itself, the tiny mechanism reveals itself. Singing sand requires a specific particle size, measuring between 0.1 and 0.5 millimeters. Particles below that threshold act like dust, clumping together and absorbing kinetic energy. Above 0.5 millimeters, grains act like rigid boulders, failing to vibrate. The surface chemistry also has to be exact. These specific grains possess a microscopic silica coating, allowing them to slide past one another smoothly without losing energy as heat. These dunes are massive collections of perfectly calibrated acoustic nodes. When gravity forces a layer of these specific grains down the steep slope of a dune, a section known as the slip face, an avalanche begins. The sand doesn't just tumble randomly. Millions of particles slide downward at nearly the exact same speed in a highly synchronized sequence. This diagram shows how that movement functions exactly like a violin, mapping physical components across both systems. The sliding avalanche acts as the bow, providing kinetic energy, while the vibrating grains act as the strings, and the massive solid structure of the dune itself acts as the instrument's wooden body, amplifying those tiny individual vibrations into the surrounding air. But there are billions of independent grains involved. How do all those tiny, chaotic collisions coordinate to emit a single stable musical frequency? This graphic demonstrates a principle called constructive interference. When one grain begins to vibrate, it forces the grains surrounding it to move in the exact same rhythm. This creates an exponential chain reaction. Rather than canceling each other out, millions of synchronized sound waves combine and stack on top of one another. That 105 decibel roar is the mathematical sum of billions of microscopic collisions firing in perfect synchronization. Earth has millions of desert landscapes, yet only a handful produce these specific sounds. The acoustic system is incredibly delicate. Even a slight increase in humidity causes water to bond the dry grains together. That moisture absorbs the kinetic energy and instantly kills the resonance. Pollution, heavy human foot traffic, and alterations to the surface chemistry cause the grains to lose their synchronization, turning the singing dunes into muted, sick sand. Researchers are actively measuring the slopes, monitoring this environmental fragility in real time to understand how quickly the system is degrading. A minor change in the environment can permanently silence a natural geological instrument that took the Earth millions of years to build. Scientists are now analyzing the specific ways individual grains transfer energy during these avalanches. By mapping the resonance of the dunes, they are developing new methods for sound control and vibration management in structural engineering. Silk Road travelers viewed these landscapes as haunted, terrifying wastelands. Today, we recognize them as geological instruments that operate with the precision of a laboratory experiment. The spirits and armies described by travelers were the result of mechanical physics. Billions of grains collide with enough force to vibrate the entire landscape. The Gobi Desert demonstrates how billions of small, synchronized actions can create a massive result. It's a reminder that some of the most complex mechanical solutions are already built into the landscape, waiting for us to listen.